Alright, this is going to be a video tutorial for Codeforces round 944 to 4 from a couple months ago. So I'm going to assume in this video and in my notes that anyone using them has read the problem statement. This Google Doc will be linked in the description of this video. All the submissions, all the code submissions are also linked to this document. So, alright, first problem, pretty simple. We get two numbers and we need to output the smaller one, then the larger one, or if they're equal, then obviously in either order. So pretty trivial, can be done in constant time, constant space. If A is smaller than B, output it first. If they're equal or A is larger, then output B first. Not much to say there. Problem B, we get a string, we need to shuffle it so that we get a new string. So first we need to determine whether this is possible or not. It turns out that the only time it's impossible is if the whole string is the same, made up of one character, the same character. So like this, for example, or this. Because no matter how we shuffle it, we can't get a new string. If it's not like this, then it's possible. So, like in this example, the only three answers that are no are this, and then this. So, the strategy we're going to do is we're going to look across the string until we see a character that's different from the first character. So in this example, we would find one right away, O. In this example, it wouldn't be until the end, Y. But once we do that, we are going to print out this character that we found, the one that's different from the first character, and then we're going to output the rest of the string while skipping that character. So we're essentially moving this character to the front of the string. So, like an example of this, if we have like this string, this is the first character that's different from the first character, H. So we would move this to the front to come up with a new string. So we would get this. So the way we would do that is we would print this character out right away, since we want to move it to the front. Then we print out the rest of the string, and we just skip this index because we don't want to repeat that since we already printed it out. So we find a character that's different, make sure we output yes, print this character out, moving it to the front, print out each character of the string in order except when we get to the index of the different character. We skip that. If we get to the end without finding any different characters, so like this or like this, we just output no. So that's in linear time, since we have to scan the whole string, and linear space as well, since we're storing the string. All right. Next problem. So there's definitely a bunch of ways to do this problem. The way I chose to do this is to see if one of the lines, I guess, one of the strings crosses the other one. So the way I determine that is if we have these two endpoints for one of the strings and we see exactly one of the two endpoints should be between this interval. Because if they were both here, like 7 and 9, if they're both inside the 6-10 interval, then they won't cross, because these are distinct. So, in order to avoid having like A and B and C and D, or C and D be greater than A and B, or anything like that, I make A less than B and C less than D, just to keep the logic simple. So if A is greater than B, swap them if C is greater than D, swap them. So yeah, in order for an intersection to exist, we have to have exactly one of the endpoints of the red string be in between the endpoints of the blue string. So if neither endpoint is in the interval, or they're both in the interval, so 7 and 9 would be both in the interval, no intersection. If we had like 1 and 4, neither the red endpoints would be in the interval of the blue string, so that's also not an intersection. So we need exactly one endpoint, not 0 and not 2. So if we get 0 or 2 endpoints, answer is no. If it's 1, then the answer is yes. So what I did was I check, is A within the interval? So A is between C and D, and then I check if B is within C and D. And I use XOUR to check that exactly one of them is correct. So these are both true, which means both endpoints are in the interval. That's not an intersection, so this will return false. It will return no. If they're both false, so neither of the endpoints are in the interval, then this will also return false, return no. But if exactly one of these is true, then we return yes. So this is done in constant time, constant space. We're only given four numbers, no matter what the size of the circle is constant. So there's that one. All right, on to D. So this is a pretty interesting problem. We need to cut the binary string so that we can sort the pieces into a sorted binary string. So all the zeros at the start, all the ones at the end. And we want to make the fewest possible cuts. So clearly, if we have like a piece like this, so let's say our string is like this. We shouldn't, like, we don't need to cut this piece. Like, we don't need to cut this piece up. Like, we can cut it out from the rest of the string, but this part should stay intact because it's already sorted. Or because it has all zeros, and we'll never need to cut out like a part from this piece. Same logic goes for all ones. So if we have this, like, this piece also doesn't need to be cut. This piece needs to remain intact. So our final string will look something like this. And we'll notice that, okay, there's all zeros and all ones, but assuming there's at least 1 0 and 1 1 in the string, if not, then, like, if this is a string, obviously we don't have to do anything, or like this. We'll have there'll be one spot where we have a 0 1. So, okay, so that's important information. We're allowed to have one of these, but we can never have, like, we'll never see this, because this would be unsorted. So our strategy is to cut out all 0 1s, cut out all, so we're cutting out all of these, we're cutting out all of these, but we're allowed one of these. So if we find three of these, we only need to break up 2 of them. And what I mean by break up is cut it like down the middle. So if we find a 1 0, we have to cut it in half and separate the 1 and 0, because this 0 needs to be moved in front of the 1, no matter what for these. For these, we're allowed to have one of them that we can leave intact, because at some point the array has to switch from 0 to 1. So let's give an example. Let's say we have this. we need to cut here. We're allowed one of these, so we ignore that. We cut here because it's a 1 0. Cut here is a 1 0. We already used our. We already have 1 0 1, so this has to be cut, and then this has to be cut. So we have to make 1, 2, 3, 4, 5 cuts. So I think the answer is actually how many pieces. So this would be 6 pieces. So how do we actually do this? I think the way I have it implemented is that I actually cut all 0 1s, and then at the end I subtract 1. So we're going to keep track of 0 1 cuts and 1 0 cuts separately, since we can't subtract any of these, but we can subtract one of these. So yeah, we're going to iterate over the string. If we see a 0 1, make a cut. If we see a 1 0, make a cut. If we had at least 1 0 1 cut, then we're allowed one of them, so we should subtract. So here I had how many 0 1 cuts did I have? 1, 2, 3. So I had 3 of each. Cut. Oh, 1 was 3. Cut. 1 was 3. We can remove this to 2 since we're allowed one of them, and then that gives us 5 cuts, 6 pieces. So add up the cuts. Add 1 since the number of pieces is the number of cuts plus 1, because we start with 1 piece, and every cut we make increases the number of pieces by 1, and that'll give us our answer. So this can be done in linear time. We iterate over this the binary string 1 time. Same with space. We're storing it. We're storing the string, so all linear space. Next problem, find the car. So car is traveling on the number line. There's k plus 1 signs, and we know the arrival time of each of these like milestones. And the car travels at a constant speed in each interval, but the speed might change between the intervals. So from here, from 0 to A1 miles, we're traveling some constant speed, but the speed from A1 to A2 is also constant, but it might be different from the speed in that first interval. So the strategy for this problem is going to be binary search. So we have to take in Q queries and output how long it takes for the car to reach that point. Okay, so we can think of this array A that they give us with the milestones as segments, a list of segments. And before we conduct the binary search on this query, we need to check 2 things. 1, if the query is before the first sign, then we don't need to check. We don't need to check anything because we can just interpolate. So, like if we have, let's say 0, 10, and let's say our 2 signposts are at like 4 and 8. If the query is 3, so what time do we get here? We don't need to do anything fancy because we already know the time here, so we just do 3/4 t. Is it? I think it's rounded down. Yeah, rounded down. So we just do this. The other case we need to check for is if it's the final destination. Because it's the final destination, so we'll call this like this. If the query asks for 8, we just return this. Pretty easy. So I think in terms of the variables they use, that's bk and then this would just be Q over A0 times B0. So we need to, those are two special cases that we want to check, because we might be able to dodge the binary search entirely. But if that's not the case, if we're not in those special cases, we need to do binary search on A. So we're going to binary search on the milestones, the road signs. There's a few ways to do it, but the way I'm going to do it is the left side tracks the start of the interval containing the queried location. The right pointer will track the end of that interval. So there's three cases in binary search, as usual. If our midpoint hits a query, so a mid is our query, then the query is on some signpost. If it's on a signpost, we know the exact time we reach that signpost, so we can just return the time we get there. Then we're done. If this midpoint of our binary search is less than the query, it means that none of the signs before mid can be the start of the interval containing the query. But mid might be. So we're going to assign left equals mid and discard all the previous signs. So in this example, let's say query was 6. If this is our mid, a mid, so mid I guess would be, or I guess let's add another signpost so it makes sense. So this would be like 2. If mid equals 1, so this is a mid, a1, then this signpost, like if Q is 6, we're not anywhere in here. And if there was another interval like here, we would know we're not in any of these previous intervals, right? Because the query has to be somewhere to the right of this, of a mid, if a mid is less than the query. So we can discard any signposts before a mid. Conversely, if a mid is greater than query, then none of the signs after mid can be the end of the interval containing the query. So if we had, let's say, intervals like 6, 7, 9, and our query was, okay, let's say our query was 5, and this is a mid, then it means that, let's say a mid was 6. We're not in here, we're not in here, and we're not in here. So the endpoint of the interval that we're actually in isn't any of these. It has to be this one or an earlier one if a mid is greater than the query. And what I mean by the interval we're in is that's what we're using left and right to find. We're trying to find the interval between signposts where our query is at. We're not we're trying to like narrow the search down to one interval. So initially it'll be like left is here, right is here, but as we search, we'll be able to narrow it down and eventually get to like maybe this interval, for example. Okay. So when left and right are next to each other, so when they're one signpost apart, that's when we know we have the final interval. There's only one interval remaining, and the query must be located somewhere inside there. So At that point, the binary search would be done, and we just have to do the calculation, the interpolation for those for that interval, and see where the distance is. So I'm going to redraw this. Hopefully, make it a little neater. So let's say this is like 0, and we have signposts here, 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 and let's say we conclude that our binary search came to this interval. So let's say our query was 12. Let's say our query was 12. So we know we're in this interval, and let's see that times for this was like 8, 11, 17. So the way we interpolate, and this is not that complicated, but we're going a constant speed in here. So we are going 17 minus 11, 6, whatever speed, we'll call it meters per second, or 6 meters. 6 meters in 5, 5 meters in 6 seconds. 15 minus 10 meters over 17 minus 11 seconds. So we're going 5 over 6 meters per second. And we need to know how long does it take us to get to 12 meters. So while we were in this interval, we're traveling 5 over 6 meters per second, and we need to travel 2 meters from the start of this interval. So that would be 10 over 6, and since we're running down, this would be 1. So it takes us 1 second to get from the start of the interval to the spot. And it takes us 11 seconds for us to get here. So that's how the interpolation is. We're finding how long does it take to get to some arbitrary point in the middle of this interval. So it took us 1 second once we got into the interval, and it took us 11 seconds to get to the start of this interval. And we have to calculate them separately because the speed inside here might be different from the speed here or here. So the answer for this would be 12 seconds to get to 12 meters. So yeah, there's a little bit of math in these notes explaining it, but I think this drawing is probably the best explanation I can give. So we'll go to the implementation. So this is just reading in the data, and we need to do this for each query. So if the query is part of the first segment, so if we are anywhere from 0 to 5 inclusive, then we can just interpolate. So if we're anywhere in here, we know we're going 5 over 8 meters per second. So we can just multiply that by whatever the distance is in the query. So if it's 3, we would have 15 over 8, so that's 1 second. If we are 5, then we would do if we're 5 meters, it would take us 8 seconds. So we could look at this, but we can also just multiply. So since our answer needs to be in seconds, we're going 8 seconds over 5 meters. Query is 5 meters. That equals 8 seconds. These cancel. So that's the one of the special cases. Second case, if we're literally at the end, so this is the final destination. If this is our query, then we just return that. So yeah. I have my implementation writes bk minus 1 as the final milestone. There's k plus 1 milestones, but I didn't include 0 in my array. That's just an implementation choice. You can do that. You can do that if you think that will help. So once we decide that we're not in the special cases, we need to do the binary search. So our starting point, since we know we're not, we already checked that we're not in this case, and we're not like right on this spot. So we know we're somewhere in this area, not including this. So our left pointer will be here, our first milestone, and our right pointer will be here. And we'll start like shrinking. We'll start shrinking the range of intervals that we have to deal with. So make our midpoint guess. If we land exactly on the query, so x is the query, then we just return the timestamp for that signpost. We return the timestamp for this signpost, and we're done. So we exit the binary search. We output our answer, exit the binary search, and then move on. Then we'll pop out back here for the next query. If a mid is less than the query, so let's say our query was like 12. We'll use the example 12 again. And this is our mid. Then it means, okay, we already checked we're not here in the special case, and we're also not in here because the query is to the right of this, so we can't be in this interval. So we'll move. So left would get moved up to here because we might be in this interval, but we're definitely not in these ones. And then same with right. And then eventually we'll converge on one interval. So when we converge on one interval, this we'll be done with this loop. We do the interpolation. We'll do the interpolation as I discussed before. So you can try to match this with what I described. So you take the time that's needed to get to that interval. You calculate the speed, or I guess it's the inverse of the speed, because like in this example it would be 6 seconds per 5 meters. So that's what this is. 6 seconds divided by 5 meters. However many meters we're going within this interval, so 2 in this case, that's what this is. And then we have to add on this, because that's how much time it took us to get to that interval. So the runtime of this is q log k, so we get q queries, and each one we're doing a binary search on the list of milestones, so that's log k milestones, so each binary search takes log k time, and we have to do that for q queries, so q log k. Space is O of k, since we are storing the milestones as well as the arrival times for each milestone, so 2 arrays of size k. Alright, next problem. So we have circle perimeters. This is an interesting problem. Basically, we need to calculate the number of points that have a Euclidean distance from the origin of greater than or equal to r, or strictly less than r. So that's what defined by this equation here. So let me clear my drawing board first. So what we're going to do is we're going to only count points for one quadrant. So actually, I think this is a good example. So it's, since it's a circle, it's symmetric, both about the y-axis and the x-axis. So if we just count one quadrant, then we can just find the points of one quadrant, multiply by 4 at the end. So we have to define what quadrant we're going to use, especially because there will be points that lie like on the y-axis or the x-axis. We have to determine, which axis we want to include into our quadrant, because we can't have both. Because if we included both, then we would have like 1, 2, 3 points times 4 would be 12, but there's only 8. So we have to choose to ignore one of these axes and just take like these points or these points as our quadrant. So I'm going to choose quadrant 1 to be anything in the top right, but nothing on the x-axis. So we include this axis, we include all the points in here, but not the x-axis. We don't have to worry about the origin. It's actually never a valid point, no matter what r is, because r can never be 0. So we never, like, the origin, no matter what the value of r is, will never be counted. So we don't have to worry about that. So the strategy that I'm going to use is, since we're only counting lattice points, so points on the coordinate plane that have integer coordinates, so like 0, 0, 1, 1, like 1.5, 2 wouldn't be a valid point. So the strategy we're going to do is, why don't we start at x equals 0, so here, we're counting the y-axis as part of quadrant 1. Why don't we find all the points on the y, or the x equals 0 axis, move to the right, do the same for the x equals 1 axis, and then do the same until we're done. That's a strategy we're going to go for. So we can think of the boundaries they've provided us, r and r plus 1, as like two arcs, essentially. So, like, let's say this is x and y axis up until 3. So let's say r equals 2. That means we're going to have an arc like this and an arc like this. So only the points inside this band count. The points can be touching this arc, can be touching the inner arc, but they can't be touching the outer arc, because we have d greater than or equal to r, but less than r plus 1. So this is 3, this is 2, 2, 3, 1, 1. So we can be anywhere inside here except touching this. So, for example, the point 1, so if we this drawing is going to be a little bit weird, but if we have this, actually, I don't know if this was the best idea, because I think this point, yeah. So this point would be valid. This point would be valid because it's on. This point is on the inner arc, and it's on the y-axis, so it's valid. This point is also on the inner arc, but since it's on the x-axis, it's not valid, since we chose to include the y-axis. So this would be valid. This point would be valid. This point would be valid. Yeah, and that's it, because all of, like, this is outside, 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 outside the band. We're not counting this one. This is this one, and these red ones are touching the outer band, so those are not valid. So we have 1, 2, 3, 4 valid points in quadrant 1. There's 4 quadrants in the graph, so our answer would be 16 for r equals 2, and yeah. So our strategy is going to be, okay, we start here. Are there any points along this line that are valid? So this one, no. This one, yes, no. Okay. And once we find an invalid point, we know there's going to be none after that because we've crossed, it means we've crossed like this thing. We've crossed the inner arc. Okay. So we had, how many valid points did we have? We had one here. Okay. Sorry for switching the colors. We moved to x equals 1. No. Yes. No. Okay. That's another one. Move here. No. Yes. Yes. Valid. Valid. Go here. No. 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 No, because it's touching the outer one. I know this one looks like it, but it's actually, it's not touching it, and we can show that since this arc is radius 3, and our distance from the origin at this point, 2, 2 is 2 squared plus 2 squared equals 8. We take the square root of that. Square root of 8 is less than 3, since this is square root of 9. So this point is actually just barely within the arc. So we have 4 points here. And once we find an x value, so here where there's no valid points, we're done. There's not going to be anything more like out here. Also, this is the outer radius, so we know we're done. Okay, so let's go to the implementation. So when we started this, we got to x equals 0. So here, how did we know at what height to start? Like, why don't we start at 10? Or why don't we start at 1? So on this axis, there's actually only going to be one point, one valid point. On the y-axis, sorry, on the x equals 0. And that's going to be 0, r. We can show that because, okay, obviously this is valid, right? Because its distance from the origin is r, and r is less than or greater than or equal to r, but less than r plus 1, obviously. The reason why 3, we know 3 isn't going to be valid is because that's the coordinate here. And obviously the distance is r plus 1, which doesn't fit within these bounds. It's equal to r plus 1. Similarly, we know 1 isn't going to work because that would be this. So then we need to check this condition. Obviously, this is not true. So there's only one valid y value for x equals 0. So we'll start our search on r, the radius. This is r. So we're going to iterate from 0, x equals 0, up until the inner radius, because on the outer radius we've shown that there can't be any valid points if x equals the outer radius. So we're going to iterate from x equals 0 to x equals the inner radius. Another thing is, whatever the highest point is on the previous x value, our current x value can't have a point higher than that. So if, for example, we have this point here is valid. This was our highest and only point for x equals 0. X equals 1 isn't going to have any points here or here or here. And this makes sense because the distance is, like if this point wasn't valid, how is this point going to be valid when it's even further away from the origin? So we know, okay, x equals 0, this was our highest valid point. X equals 1, we can just start looking, we can just start searching here because we don't have to worry about anything higher than it. and we're going to update this for every x coordinate. So this is a bad example to show it, but for here, so this is what, 1, 2, 3. Our highest is 3, so we can start a search at 3, 3, 3, 3. Okay, invalid 2, and then if there were more x's for us to check, we would just start at 2. Okay, so we're going to move downward until we're in bounds. So in this example, 3, we're starting at 3, starting at 3, starting at 3, valid, valid, valid. Here we start at 3, and we say, okay, we're not in bounds, so we have to move downward until we are in bounds. So we decrement until we're in bound, so 3 down to 2, okay, we're within the band. And we mark this as the new h start. So this is the update I was talking about. So if there were more columns for us to start, we say, okay, just start at 2. Y equals 2 next time. Next is we need to walk downwards until we're inside the inner arc, which is out of bounds. So once we're in bounds, we walk downwards until we're out of bounds. So valid, valid, invalid. And then that's like, we add that to our count of valid points. And we just do this for every x value from 0 to r. So in this case, 0, 1, 2. Count up our points, multiply them by 4, and then that's our answer. So I guess this explanation was a little maybe not the smoothest. So you can feel free to leave any questions in the comments, but hopefully that plus the drawing plus the code help shed some light on that. So there's little extra details in the notes if that will help you. The runtime of this solution is O of R, since we're essentially searching the perimeter of the band. So like we're essentially just walking inside this band. And this perimeter is so the whole circle would be what, pi r, or 2 pi r, and we're doing 1 quadrant of that. So we're searching like this much. So the actual area of what we're calculating is, so the outer radius would be pi r plus 1. Or the actual the area of the circle caused by the outer radius would be this, pi r squared, minus, and then this would be the inner one. So we would have r squared plus, what, 2r plus 1 times pi minus pi r squared. So that gives us, so this cancels, or this cancels. So we have pi 2r plus 1. So this is the actual area on the graph that we search. So that's obviously O of R, linear. As for the space, it's constant. We're only storing like a couple local variables here. So constant space. Yeah. All right. Next problem, G, XOUR. So actually don't have my submission for this. Let me add those to the document real quick. All right. So XOUR, I guess it's supposed to be. So yeah, let's start by looking at this fact XOR. We can swap two elements if their XOR is less than 4. So what does that mean? Like, why is that useful? So let's say we have some random number, let's say like 73. So in binary, that's 64 plus 8 plus 1. So 64, 32, 16. So this is 73. Yeah. Let's say we have 85. So 85 is 64 plus 16 plus 4 plus 1. Oh, okay. So, yeah. If we XOR them, what do we get? So the XOR, bitwise XOR goes here. So are these the same? Yes. So this is 0. Same, 0. Same, or different, 1. Different, 1. Different, 1. Same, 0. Same, 0. So this is the XOR. And that is equal to 4 plus 8 plus 16 is what? 28. So 73 XOR 85 equals 28, which means that 28 is obviously greater than 4, so we can't, like, we wouldn't be able to swap these elements. So what we notice is that, okay, this bit is equal to 4. So if the two numbers have different bits here, then our XOR is going to be at least 4. Or if they differ here, it's going to be at least 8. So our XOR has to be less than 4. So it means that this bit has to be the same, this bit has to be the same, this bit has to be the same. All of these have to be the same except these two. These are the only two that are allowed to be different than each other if we're going to be able to swap these numbers. So if we have like A equals 0, 0, 0, 1, 1, 0, 1, 1, 0. If A and B are swappable, all we know is that this part of A has to be the same as B. So we know this, and then it doesn't matter what B is here. We could have like, it could be anything, 0, any of these would work. But this part of the binary representation has to be the same if the two elements are compatible for swapping. Okay, so we want to create the lexicographically smallest array made with any number of swaps. So these would be swappable. What are these actual numbers? What is this? 2, 4, 8, 16, 32, 48, 52. So this is 54. And then let's say this is the actual value. So this would be 55. 54 and 55 are swappable. And obviously, we would want to put 54 first. So if our array looked like this, we do our calculation, say, okay, 55 and 54 are swappable. So our final array should be this, because we want the smallest possible values in the front. That's the definition of lexicographically smaller. So how do we actually, like in the code, how do we actually determine, oh, these two elements are swappable? So we've just said that this part does not matter when it comes to whether two elements are eligible for swapping. We only care about this part. So if that's the case, then we essentially can cut off the last two bits and save the rest. So let's say we have 47. So that would be 32 like this. 47, let's say we had 45. So that would be this. So we don't care about this. We just want this. So these two are swappable. We're essentially chopping off the last two bits, which means we are dividing by 4. because we're essentially shifting this down by 2 bits. We say we don't care about this. We just want to turn this into this, and then this into this. So they're the same. So that means they're swappable. So this is the same as dividing by 4. So a equals, it's like a divided by 4 rounded down. We'll get rid of this part, or a shifted to the right by 2. Either one works. So you want to do this for both numbers, and the result should be the same. So if a divided by 4 equals b divided by 4, can swap. Else cannot swap. Okay. So we're going to have different groups of numbers that can be swapped, and some that can't. So we just said 47, 47, and 45 are swappable. And then we also said 54 and 55 are swappable. So these can be swapped, these can be swapped, but these can't be swapped with each other. Like 47 can't be swapped with 55 because 47 divided by 4 rounded down is 11, 55 divided by 4 rounded down is 13. So these are different. So this, we can't swap these. So what we're going to end up having is we're going to have a bunch of groups of elements that can be swapped amongst each other within a group, but not like not between groups. So you may have been able to tell already. So okay, this is one group. This is another group. This is another group, and so on and so forth until whatever number. Now, this is a ton of data to store, especially because AI can go up to 10 to the 9. So we can't store 10 to the 9 over 4 groups. So what we're going to do is we're going to assign all the elements of the array to a group ID. So we said 47 divided by 4 is 11. So these elements are part of group 11. This was 13. So these elements are part of group 13. So we're only going to keep track of groups where they have elements in the list. So if our array was like this, we will keep track of, okay, we have some stuff from group 11 here, we have some stuff from group 13 here. We're not going to store data about like all other groups, so there's no elements like from this group, so we don't need to store anything about that. So basically we're going to construct a map where this is the key, and then we're going to have a vector of all the members from all the elements from the array that are in this group. So let's go to the implementation. So read in the data and make this map. So when we come across an element, for example 54, how do we know which group it's in? Divided by 4, round down, 13. Okay, so it's a part of group 13. We have this group structure here, so it contains a few things. One is the ID, so that's what we're talking about here. 54 belongs to group ID 13. Index, we'll worry about that later. And members, so this is a list or a vector of all the members, all the elements in the input array A that fall into this group. And there can be duplicates as well. So if we try to get to the group ID, and it's -1, it means, okay, this element is the first element for this group that we've seen. So when we're iterating here, we haven't, this is the first element of group 13 that we've seen, so we need to create a group, add it to the map, and then add our element to that, so add 54. And then, yeah, put this group in the map. If it already exists, we just need to add our element to this vector. So when we get here, this is also part of group 13. Group 13 already exists in our database, so it would be like this at this point. We just need to stick that there. Okay, so we also want to, in our final array, we want to have the smallest possible values as far to the front as possible. So it means that for a certain group, within a certain group, we can swap the elements, and we want to swap the lower ones as far forward as possible. And what this means is that, let's just say, is there a good example here? Yeah, this is a pretty good example. Let's do this. 2, 7, 1, 5, 6. So let's say we go, so we'll keep track of our database here. So what is this? This is part of group 0, right? Because this is 0. So at 0, we have a 2. Okay. What group is this part of? 1. Okay, we have a 7. What is this part of? 0. Okay, we already have group 0, so we add 1. This is part of group 1, 5. Group 1 also 6. So basically, this is our final array. So we need something from group 0 here. Group 0, because 2 is part of group 0, so it can only be swapped with other elements of group 0. We need something from group 1 here, group 0 here, group 1 here, group 1 here. So this is our final array, so we need to put stuff in like this. So clearly, okay, why don't we just say, let's worry about group 0 first. So the 1 should go here and the 2 should go here. We move on to group 1. Okay, we should put the 5 here, the 6 here, the 7 here. So that is indeed the answer. So how do we actually implement this? We don't actually want to go this route where we go, okay, let's do all the group 0s, then all the group 1s. Because then we'd have to search the entire array for group 0s, and we have to search the entire array for group 1s. So we're actually just going to go like this and do them all at once. So we say, okay, we need something we want the smallest group 0 element we have. So in this case, that's 1, but we don't want to have to search through this whole thing every time. So we're going to sort these. Before we construct the final array, we're going to sort these. So that would make this. Okay, now we can get to work. So we say, okay, we need our smallest group 0 here. So that's obviously 1. Now that we've used 1, we can't reuse it unless we have another 1. So we are going to move, that's where this comes in, index. So initially the index is 0 because we haven't used any of the elements. So initially we're here. But when we move the 1, when we use the 1 and add it into our final array, we need to increment this. Because this is the next smallest element we have remaining. This one, we've already used it. We can't use it anymore. So that's what this is down here. Yes. Okay. And then for this group, their index is here. So we need the smallest one from group 1. Okay, group 1, index pointing to the smallest element, 5. We've used this, so now we're pointing here. Group 0, what's the smallest thing we haven't used yet? 2. Okay, done, so the thing would be pointing here because we have no elements left. Group 1, smallest left is 6. move up to 7. Group 1, smallest thing we have, left 7. Done. So construct our map of groups, adding all the elements into it. Sort each group individually. So we sorted this individually to 1, 2, sorted this individually to 5, 6, 7, and then iterate across here, checking what which group each index belongs to. And we can use the original array for that. So this is the original array. We can just check, okay, what group does index 0 belong to? Oh, there was a 2 there in the original one, so that must be group 0. We can just do this quick division to check. So yeah. Original value in the original input array. Figure out the group. Here. I'm actually not sure why I did this. I multiplied every group by 4. That doesn't actually matter, because then instead of groups 1 to instead of groups 1, 2, 3, 4 like 0, 1, 2, 3, 4 like this, I would have groups like this. Group numbers like this. That doesn't actually matter. But find the group, get the list of elements. And then get the index of the ones that we haven't. Get the index for the next smallest element of that group that we haven't used yet. And then make sure to increment after we use it. And then we can just write back into the original array, because we don't need, once we write to an index, we don't need that index. We don't need the original value anymore. Then it just remains to output our final array. So now for the time, n log n, we need to create O of n groups, since potentially each member could be in its different groups. If we had like, if we had like 1, 10, 20, 30, these would all be in different groups, clearly. So we might have to create up to n groups. Inserting each group into the map takes log n time, log n operations for maps. So n log n time for this step. We need to sort each group amongst itself. So sorting is n log n, where n is the size of each group that we're sorting. But we might have all the elements in a single group. So if we have like 1, 2, 1, 1, 3, 1, 4, 2, or not, I guess 4 would not be there, 0. This is all one, the whole array would be one group. So we would potentially have to sort all n elements together. So that would be n log n. And then we need to assemble the final array. So we need to make n, we need to access the map n times. And each of those is log n. So this step is also n log n. So n log n plus n log n plus n log n. N log n total time. O of n space, we need to store the original array, but we also need to store the individual groups. So the amount of space taken up by the groups is how many groups do we have, because there's some data that is stored for every group, and then the total number of elements in the original array, which is n. So total number of elements in all groups plus number of groups. These are both, this is n, this is O of n, so we're taking O of n space. Alright, last problem. This is a pretty interesting problem. I definitely had to do some learning for this one. But yeah, so in order for Alice to win, she needs to be able to assign at least 2 out of 3 of each column to be +1. Because if the middle row has to be all ones, then that means there's at least 2 ones in each column. Because if there were 2 -1s, then the middle one would be -1. If there were 0, then they would all be -1. So she needs to come up with some sort of assignment to map her array with, such that there's at least 2 +1s in each column at the end. Okay, so we can reformulate the basic overview. What we're going to do, high level overview, is we're going to reformulate this grid as a 2-sat problem. We're going to construct an implication graph based on the clauses generated from our 2-sat formulation. We're going to run Kusaraju's algorithm to find strongly connected components. So what that means is a strongly connected component is a set of vertices in the graph where there's a path from to and from any 2 vertices in the graph. So there has to be, in order for 2 nodes to be in the same strongly connected component, there has to be a path from node A to node B and from node B to node A. And then we're going to examine the strongly connected components once we find them. So the first step is formulate as 2-sat. So like I mentioned, she needs to have at least 2 of the 3 entries in the column to be +1. We need to figure out if this is even possible. Pretty basically, that's the whole problem. So in order for a column to have 2 out of 3, it means that we're gonna treat, by the way, 1 is true and -1 is false, just for simplicity. So, like in this example, Bob's grid is like, okay, this value will get converted to Alice's first input. This will get converted to the opposite of Alice's 4th input. So if Alice's 4th input is false, then this whole thing would be evaluated to true. If Alice's input for her first input is false, then this would be false. If her input is true, it's true. So from looking at this column by itself, it's obvious that A1, Alice's first input, has to be true. So these are both false. If these are both false, then we have 2 out of 3 inputs in this column, 2 out of 3 variables in this column that evaluate to false. So she wouldn't win in that case. So A1 definitely has to be true, and then, we'll see about the later ones. So 2 out of the 3 have to be true, have to evaluate to true at the end. So if we have variables A, B, and C, I'll draw it like this. So we have variables A, B, C. We need 2 out of 3 have to be true, at least. So what this means is, if at least 2 of them are true, it means if I take these pairs, at least one of these from each pair has to be true. So for A and B, at least one has to be true. And at least one of B and C has to be true. And at least one of A and C has to be true. This is pretty intuitive, because if for any pair, let's say this pair, B and C are false, then we can't have 2 out of 3 be true if 2 of them are false. So we basically need this statement. We need this overall statement to evaluate to true. So we need we need A or B, and we need B or C, and we need A or C. So we can use this to construct clauses for our two-set problem. So the way we do that is, okay, if we need A or B, what does that mean? It means if we don't have B, so let's say B is false, then A has to be true. So if not B, then A. Also, it goes the other way around. If not A, then B has to be true. Otherwise, both are false, and then we fail. So we can construct that for all of these. Okay, so this gives us 6 clauses. And we're going to do this for every column. So in here we would have A1, or not, I'll just do this, not A4, A1, or A1, not A4 or A1. So obviously this is like, there's some redundant ones in here. Actually, I'll go to the next column. Oh, the next column, so there's no like repeated ones. So we have not A2, or A4, A4 or A2, A2 or not A2. Okay, so we construct the clauses. So not A2 means A4. So if A2 is true, that means this is false. So if this is false, then we need this to be true. So if A2, then A4, and it goes the other way around too. So if A4 is false, then we need not A2 to be true. If not A2 is true, A2 is false. So like this. Repeat this for here. So not A2, we need A4. Handwriting is so bad. Not A4, A2 is true. And then same for down here. A2, if we don't have A2, then we need not A2. If we have A2, then we need not A2. So obviously, you can see that this part is always true. Like this one will always be true. So it doesn't matter. So we'll do this for, we'll construct these statements for every column. So we'll do it for this one, this one, this one, this one. And we need to turn this into an implication graph. So how do we do that? So an implication graph is every variable you see here will have its own vertex in the graph. So this is a vertex, this is a vertex. We already have a vertex for this variable. This is a vertex. So we have, for these statements, there'd be, well, there's also one for here. Yeah, sorry. So 1, 2, 3, 4, and then all the ones down here. All of these are just like repeats. So we have 4 vertices. So A2, not A2, A4, not A4. So obviously we're going to have more vertices than this because there's other columns to consider, but I'll just draw the implication graph just for this set of 6 clauses. So we said A2 implies A4. So what that means is there's going to be a directed edge from A2 to A4. So that's this. Okay. A4 implies not A2. Not A2 implies A4. Not A4 implies A2. Not A2 implies this. So this goes here. Alright, I did it backwards, I guess. We have this. Right. So yeah. Actually, Actually, I made a mistake here. So these ones I have backwards. So if not A2, if we don't have this one, then we need this one. So it's actually like this. And if we don't have this, if this is false, so this would be not, if not A2, then we need A2. So this should just be A2. So the graph here would actually be like this. Okay. So if we had this, this would be an immediate contradiction. We'll get to that. Okay. So this is the implication graph. And what we need to do now is we need to run XOUR's algorithm. So that basically finds all the strongly connected components. Before we get to that, we need to discuss why is that significant? And the answer is it's significant because if a variable and its negation, so A2 and not A2, or A4 and not A4, if they're in the same strongly connected component, it means there's a contradiction. And if there's a contradiction, it means there's no way for Alice to come up with this array so that she can win. So if there's a contradiction, it means Alice loses. If there's no contradiction, she wins. So contradiction comes from if there's two variables that are negations of each other that are the same strongly connected component. We mentioned before, same strongly connected component means there's a path from A to B and from B to A. So, for example, is there a path from A2 to not A2? Let's see, this way doesn't get us there. This way doesn't get us there. Okay, so there's not. Okay, what about this pair, A4 and not A4? We can't leave. There's no way for us to leave this node, so there's no. So this, there's no contradictions in this graph. But what I said earlier, if we had, when I wrote the statements incorrectly, if we had this, this would be an immediate contradiction. So we can get from A2 to not A2, we can get from not A2 to A2. So this would be a contradiction. Because basically what we're saying here is, okay, if this is true, that implies this is true. But that, like, and if we're saying this is true, then this implies this is true, which isn't possible since they're opposites. Okay. So we have our graph, and again, this would contain many more nodes and edges since we have to do this for each column. So we'd have one big graph with everything there. So, okay, XOUR's algorithm. So we're going to run depth first search on the graph, and we're going to add a node to the stack when its DFS concludes. So, if we started our DFS here, we would say, okay, A2. So this would, let's say our stack is here. So we go DFS A2. Okay, then we go, okay, DFS A4, because that's in A2's subtree. Okay, we call DFS A4, nowhere to go, done. So A4 would go on the stack. DFS A4 returns, DFS A2, okay, nowhere else to go. A2 on the stack now. Okay, these nodes are done, go here. Not A2, so DFS not A2. We already searched here, so this is done now. So we go not A2, and then not A4 would be the last one. So that's step one. The next step is we need to have a graph where all these edges are reversed. So it's called a transposed graph. So this would switch to like this. this would switch to this, like this, this, and then these edges wouldn't change, but they don't matter anyway. So now we need to run DFS on this transposed graph, red edges, but we want to start at the top of the stack and work our way downward. So this was the last DFS to finish, but we want to start with it this time. So we say, okay, not A4. Can we go anywhere with the red edges? No. Okay. So this is strongly connected component 1. So A4 is part of strongly connected component 1. Can't go anywhere though. Okay. So we pop this off the stack. This is done. Now we go here. A2. Is A2 assigned a component yet? No. So that's strongly connected component number 2, because it's not in the same strongly connected component as not A4, because there's a path from A2 to not A4, but not from not A4 to A2. So this is its own. Pop this off. Okay, now we're here. Or I guess we were down here. It doesn't matter. They're part of different connected components. Strongly connected components. Anyway. So here, nothing assigned yet. 3, and then it turns out they're all part of different strongly connected components. So if we had a situation where, like, let's say, we'll just only worry about the red edges. Let's say we had this. So these two would be in the same strongly connected component because there's a path from this one to this one and this one to this one. So which one got popped off the stack first? A2. So let's say we A2 was like, we assigned it a strongly connected component 3. When we run our DFS, any node we touch on the DFS will be part of the same strongly connected component. So this is not the best example because none of them are, but like if we come across a component, or we come across a node in the stack that already is assigned a strongly connected component, then we'll just pop it off the stack and don't worry about, we don't want to modify its assignment. And that would happen if we encountered it on a DFS on the transposed graph. So if we, like, let's imagine our stack was like this. We start here, okay, nothing assigned yet, strongly connected component number 1. DFS, run DFS on this node now. Okay, we found another node. Okay, not A4 is part of the same strongly connected component. So we would assign this also to 1. And then when we get down here in the stack, we say, oh, it's already been assigned to an SCC, pop it off, do nothing. So I kind of mixed up a few things there, but hopefully that makes sense. And my notes here should be a little bit better. So, like we mentioned before, the strongly connected components, the implication is if we have two variables that are negations of each other, so these two or these two, and then the same strongly connected component, Alice cannot win, so our answer is no. Otherwise, our answer is yes. There's no contradictions. Okay, let's go to the implementation. So that was a lot of information. So, I guess I'll start at the top and go over like the data that I'm maintaining. So this is our graph, adjacency list, and another adjacency list for the transposed version of this graph. My implementation doesn't go through and actually flip the edges after the first DFS. After this DFS, it doesn't actually transpose the graph. I just built both of them at the beginning. The original graph and the transposed graph. This is our visited lookup. So when we run the DFS, Depth first search, obviously we have to keep track of which nodes we visited. Finish, so this is the stack that I was talking about. So in the first DFS, we need to keep track of the elements in reverse order of when their depth first search finishes. So this is a stack. We'll use this as a stack to add our nodes to when their DFSs finish. And then components. So this is a lookup table where we assign nodes to their nodes/variables to their strongly connected component. Okay. So we take in our input here. Since the data is global, we need to, every time we have a new test case, so like this is one test case, this is one test, one test, one test, we need to like reset all of this data to reinitialize it, basically. The scheme that I use to keep track of nodes, so each node has an has an integer number that's the ID of the node. I'm going to have it like variable 1 is node 2, and then not its negation will be node 3. So if we have variables like let's say this, this would be 2, and then not a1 would be 3, 4, 5, 6, 7. You get the point. And then 0 and 1 are unused. So there won't be like any actual nodes with that. So we need to make our 2 sat clauses. So that's what this is. We say, okay, for this column, which nodes and which edges do we have to draw? So, it's the wrong one here. So we said 2 implies A2 implies A4. So which one is this? Which node is this? This is node 4. This is node 8. So we need an edge going from 4 to 8. So yeah, so this is var1, var2, var3. These are the variables for each column. If it's negative, then we want to have the negative version. So if, let's say it's 2, like this, then if var1 is a2, then so it would be negative 2, then its node number would be 3. If it's positive 2, then it's 8, or it would be 5, I guess. 2 times absolute value of 2, 5. If it's positive 2, then 4. So this gives us a mapping of from this particular column to which nodes we have to deal with. So this is constructing the graph. What did I say? We need an edge from 4 to 8. So n here is a macro I wrote that is like the negation. So we're just flipping the last bit, right? Because 2, 2, and 3, we're just flipping the last bit. 4 and 5, the last bit. So this just quickly gets us the negation of any variable. So not var1 implies var2. So edge from not var1 to var2. So for this column, this is var1, this is var2. So if not var1, if not a2, then a4, var2. So that's what this is. Let me just do the same for all this. And I have this, if not var1 happens to be the same as var2, so like here, this and this are the same. This and this are the same. We don't want to like worry about adding those edges. So like this wouldn't actually exist like in our graph. Simultaneously, we build the transpose graph. So we basically just reverse all of these. So instead of drawing an edge from not var1 to var2, we draw it from var2 to not var1. Okay, graphs constructed. We run DFS on the normal graph. So for each node, if it's not visited already by a previous DFS, then we visit it. This basic DFS function. Mark the node we're at as visited, and then for any unvisited neighbors, recursively call this function. And once a particular node's DFS is done, we want to put it on the stack. So that's what we're going to do with this. Okay, this is done now. Go to the transpose graph, so this, and we need to run DFS on the nodes in reverse order of how they finished. So finished, we're going to iterate backwards, get the node on the stack. If its component assignment in the lookup table is -1, it means this node is part of an SCC that we haven't seen before. So we're going to so this will increment every time we encounter a new SCC. So assign, this is basically a DFS also, except we're assigning components. So assign to the current number for all its neighbors in the transpose graph, assign them to the same SCC. And then repeat that until we'll have all of the nodes assigned to an SCC. Now we just have to check, okay, is there any element and its negation, or any variable and its negation that are in the same SCC. So we just simply iterate over all the variables. We say, okay, this is a variable and its negation. If they're in the same component, then there's contradiction. Alice can't win. Print no. Otherwise, there's no contradiction, so she can come up with an array to win. So as for time, building the implication graph takes O of n time because there's n columns. Each column gives us 6 clauses, so that's 6 clauses, 6 edges to add to the graph, so 6n edges. So that takes O of n time. Codeforces algorithm, the first DFS on the original graph, and then the second DFS on the transpose graph. DFS runs in O of v plus e, vertices plus edges. Both of those are O of n, so each DFS runs in O of n. We run 2 of those. So this step is also O of n. Then the last part is we need to check the SCCs that we assigned in Codeforces algorithm. So we just need to check each variable and its negation. That's also O of n time. So O of n time in total. We keep track of a bunch of data. So these 2 graphs are both O of n space, since there's O of n edges. These graphs take up space equivalent to O of v plus e space. So we have n vertices and n edges, so each of these graphs are O of n space. This is O of n space, O of n space. This will take up O of n space as well. So O of n space required to store all of our tables, vectors, the stack, component assignment, etc. So O of n time, O of n space. Yeah, so that's gonna conclude the tutorial for this contest. It was a bit all over the place. Some some higher level difficulty problems than I usually do. I tried to not go super low level when it comes to describing every step of the higher level problems, but I also wanted to give a little bit of detail to people who are maybe just starting and want to attempt these problems. First video in a while, so it's a little bit disorganized, but hopefully these explanations are still helpful, and hopefully tighten up and clean up the explanations in future videos. So yeah, you can always leave a comment on the video asking a question, and I'll get to it as best I can. You can message me directly on Codeforces as well. That's an option. But yeah, any feedback, leave a comment, add me on Codeforces on Bean Burrito. Whatever you need to do to let me know if you have a question. I'll try to explain it as best I can.